Right, well, good afternoon, everybody. What I'd like to do now is to move away from talking about OR and to talk about a completely different platform, although I will have one slide which will actually integrate the two different ideas. So I want to talk to you specifically about something called Hadoop, which is a specific platform that's been designed for analyzing very, very large data sets. So it's something of the poster platform for big data in general. Again, just to note, here's my web address. And again, if you have any questions and if you want to follow up, please email me or indeed just tweet me. So just to give a brief outline of what I'll be talking about over the next hour or so, first of all, I just want to precisely explain what do I mean by Hadoop. Um, what I'll also do is then move on and talk a little bit about how data is stored. And then I want to actually spend some time talking about the different components that lie within Hadoop. So in particular, I want to talk about something called HDFS and Yarn. And I know that this is in some respects sort of really kind of unpacking what's going on underneath Hadoop, and it may not be necessarily of direct interest to you, but I think it's if one is going to actually go and make use of Hadoop, it is important to understand a little bit about the elements of what's going on there. All right. Once I've sort of explained that, then HDFS and Yarn, then I can get on to talking about what I guess is the heart and soul of Hadoop, which is MapReduce. So, and again, the point to make clear here is that MapReduce is not the same as Hadoop. All right. MapReduce is a subset of Hadoop, but it's what you might say it's a really, really important subset. I'm going to spend one slide. So, having explained MapReduce in fairly considerable detail, I'm then going to move on and talk about something called Pig and Hive, which are just one slide to explain that, which is a very neat idea, which sort of which makes use of MapReduce. I'll also spend another slide talking about something called or Hadoop. At least I think that's the way it's pronounced. And then what I also want to do is spend some time also talking about an implementation that myself and my graduate student, Jamie Al-Nazir, have been doing to basically use Hadoop to actually analyze a particular type of data set. And then at the end, I haven't put that bulletin in there. I'm going to do a sort of a shameless discussion if I have the time. Okay, so again, I just want to make a few sort of introductory notes. The first one is this: is I want to thank Gregory Chokla, who's also based at Royal Holloway. Much of the explanations of how MapReduce work and so on are based on his lecture notes that he provides on Hadoop and so on. And again, I want to stress that this is largely an introductory talk. I'm going to make the assumption that the audience here, that you actually haven't run anything on Hadoop before. If you have done something on Hadoop, then you're probably going to be somewhat disappointed, and you may even know more than me about it than I do. The other point I haven't bulleted here, but I will also make clear, is that I'm not going to spend time motivating why it's important to look at big data. I think this entire conference is thinking about big data, so I think it's sort of kind of blatantly clear that we all have to deal with hundreds of gigabytes, terabytes, and so on of data, and it's just going to continue to roll up. Okay, so first of all, again, let's ask the question: what exactly is Hadoop? All right. So it's a software library which sets up a framework so that you can do distributed processing of large data sets across clusters of computers, and you can do so using simple programming models. In fact, uh, at the end of the day, what you end up with is you can either do things directly on the command line using the, the, the Hadoop interface, or you can write things in Java. All right? Now, Hadoop, which is written by the open source collaboration Apache, they provide basically four major software components. Right? So there's Hadoop Common, which are basically sets of tools that they all need to use. Then there's the Hadoop Distributed File System, or HDFS. And then there's Hadoop Yarn, which stands for yet another resource negotiator. And then finally, there's Hadoop MapReduce. All right. Apache are also working on a bunch of other related projects. So, for example, Pig and Hive, which I've mentioned before, is there, and also Mahout, which is a set of machine learning libraries which sit on top of MapReduce. Again, just like in OR, all of this is available at an open source level. So there's, it's all there, it's all freely downloadable. Go make as much use of it as you possibly can. I should also note that, again, there are lots of commercial providers who are also providing things which sort of sit on top of MapReduce and Hadoop as well. Okay. So the next thing to ask is, well, what does it run on, and what is it for? Okay. Well, if you wanted to, you could probably download Hadoop and run it on your own laptop. Certainly, probably a good idea just to test things as you wish. Obviously, what you want to do is you want to do that for something a little bit bigger than a laptop. So you want to actually start looking at running this on particularly set of cluster of computers. All right, whether that be 5, 6, 7 computers, or if you're scaling up to something much bigger, like you have a whole data center. All right. So in particular, the sort of motivation behind Hadoop is it needs to be it should be run on large networks of cheap commodity machines. Okay, which are connected up with each other. All right, and that you can connect up via SSH, for example. Now, examples of the kind of cheap commodity machines that we're talking about, of course, you could go to your major provider like Dell or whatever, and they'll sell you your racks. There is an interesting open hardware initiative called Open Compute, which is actually coming from the people at Facebook. And the whole idea there is they're saying, okay, well, this is how you build the kind of commodity machines which are there out of the components that are available, so you can set up your own racks and basically set up your own data centers. As for actually configuring Hadoop, in the last few days, there's a very nice little introduction on all the various bits and pieces that you need to go about and actually set yourself up on Hadoop, and I've given that there on an hourly address. Now, if you don't have your own 10,000 processor data center to hand, or indeed if you have difficulty getting access to a multi-core cluster, one of the things that's very nice is the fact that many of the cloud providers now, for example, Amazon and Microsoft Azure, and also checked Rackspace as well, they allow you to set up your own set of instances that will run Hadoop. So particularly for Amazon, it's Elastic MapReduce, and for Microsoft Azure, it's HD Insight. So, and as an example of that, we can go and look at here. So, for example, if you have yourself an account that's set up on Amazon in this case, but as I said, it could be Azure, it could be Rackspace, it could be a number of different guys. You can set yourself up with your own instance, so with whatever number of clusters that you want. And again, given the interface that you have, you can now run whatever set of jobs that you want on it. Of course, running on the cloud presents a difficulty. In particular, you have to now say, well, how am I going to upload the data that I have there? But that's another issue for another day. Okay, so let's get back to this now. Okay, so Hadoop, in particular, is with respect to we've seen what it runs on. Now let's ask the question, well, what's it for? And of course, it's about analyzing very, very large data sets. So we want it to be scalable up to potentially petabytes of data. This is the framework that, for example, Google were using to analyze their data. And if you note that they're going through about 10 to 20 petabytes of data every day. And in particular, one of the things to note is that the data that they have is very, very large, but it isn't stored in anything like some sort of standard relational database. All right. Generally, this information is coming to them as huge numbers of flat files. All right. And in particular, the thing they are interested in is the type of analysis they want to do is online analytical processing, or OLAP. All right. So in particular, what they're interested in is just saying they want to do throughput-oriented applications. In other words, here's my data set. I want to go through every possible entry in there and find something about it. Okay, find me all the occurrences of the phrase Kim Kardashian on all the web pages that we have stored. All right. The data that we have is typically write once, all right, or there's something which is added on there. And then most of the time what you're doing is you're then going back and reading that data, okay? What's interesting, of course, for anybody in this room is that that's very much the kind of model of the data that we have for most research data sets. In other words, typically what happens is that the data, we store it, we generate it, it's stored, it's kept, and then what you want to do is analyze every the data set, look through every instance of the data, and read through it many, many different times. Right? So in that respect, it's one of the reasons why this approach is one that's of so much interest to researchers. Now, getting back to the issue of I sort of talked about this idea of saying, okay, we're dealing with clusters of computers and data centers. So you're dealing with potentially thousands of computers, right? And these computers are built out of standard commodity components just coming off the shelf, right? Now, these components are built as economically and as in as cost-conscious a fashion as possible. What that means in reality is that if you've got thousands of components that you're going to be working with, and even tens of thousands of components that you're going to be working with, all built in as economical a fashion as possible, but you have to accept that failure is always an option. In fact, it's inevitable. So, for example, Jeff Dean, who works at Google, has a set of slides talking about this, and he lists, when you're looking at a new data center, here's the sort of chances of different sorts of failures that you're going to get in the first year. So in later years, it's going to come down a little bit more. He doesn't actually explain by how much it goes down, but it still gives you an idea of what's going on here, all right? So he said, okay, 1,000 individual machine failures, thousands of hard drive failures, rack failures, racks go wonky, so 4080 machines see 50% packet loss, all right? Half of them will just overheat, and of course, controlling the power, controlling things from overheating is an incredibly difficult problem for data centers. All right, so you have to accept that failure is an option. It's inevitable. These components, things are going to go wrong with them all the time. All right, and hence, with any system that you design, it needs to just accept that and live with it. The other thing to note is, as you said before, data sets are getting bigger and bigger and bigger, just relentlessly increasing. And that again presents challenges. You might want to say, oh, okay, you know what? If I'm going to be dealing with all of these cheap computers which are just falling over all the time on me, then maybe what I should do is my money would be better spent on doing things, on buying very, very expensive pieces of kit, let's say shared memory architectures, and then really they run really fast and they don't fail because they're built by Cray or whatever, and just work with those components. Well, the problem is that it's a complete non-starter. All right. So if, for example, there's this command called grep, which exists in Unix, and what grep does is it says, okay, here's a single word that I'm looking for in a document. Show me all the lines where this word turns up. Okay, so if you're running that on your own computer, okay, admittedly this is about 10 years old, so all of these figures are going to be rounded down by quite a large factor, but still, if you're going to do a single grep, if you're searching a megabyte of data, that takes a second. If you're going for a gigabyte, it's a minute. A terabyte, 2 days. Petabyte, 3 years. All right? Now that's if you're doing a single run with a single processor just churning right through it. Of course, instead of trying to say, oh, okay, spending 3 years trying to do a grep on a petabyte of data, what you do instead is you have 1,000 processors dividing that petabyte up into 1 terabyte, or indeed looking at 1,000,000 processors and dividing up into chunks of 1 gigabyte, and then again doing the graph, and then putting all of that together. All right. So parallel computing is a huge field. It's a field which has been around for 30, even 40 years, and it thinks about some very, very hard and complex problems. But the thing to note here is that much of the analysis that can be done in a really totally trivial sort of way. In other words, a recipe is, here's my data set, break it up into chunks, equal size, and then I have lots of processors which go and analyze each individual chunk. So in other words, the length of my problem gets reduced effectively by the number of processors that I'm working with. Okay, so you can make a huge difference in that respect. Okay, and this is the idea that we have here. So we have some big amount of work that has to be done. We break that work into a bunch of different chunks, in this case, into 3 different chunks. Then we've got some sort of 3 different workers which go and just work away completely independently of each other. So this worker works in this data set W1, this guy works on W2, this works on W3. They just churn right through their individual data sets running in parallel. They generate their results, and then those results, which are usually much smaller in output than these top 3 inputs, they're all merged together to produce your result. Now this is all an extremely schematic way of doing things, but it's a surprisingly common way of doing things. All right, and there's something that should be made clear, is that this is, again, in no way, shape or form rocket science. In many respects, this is precisely the way the batch mode of analysis works. So you take a whole bunch of processors, and they just say, okay, divide it up into, partition my data set up into chunks, and then each processor deals with some chunk of the data, right? and you're able to just scale up really quickly. Okay, so once you can combine all your results. So parallelization is absolutely key here. Okay, whatever system you have to analyze these very large data sets, you need to get parallelization. As I said, your components, they're cheap. Okay, so failure is always an option, right? And hence, what we have to do to deal with that is we have to do two things. All right. Again, the solution is to make use of massive parallelism. All right. Again, to say, well, I accept that my components are going to fail. So what I'll do is I'll have so much replication that actually I won't miss out on anything. All right. So, and that happens at two different levels. The first one is your hard disk drives can fail. So, okay, we'll have huge amounts of replication. And we've seen this already. This is something which we understood well from, from the RAID method of storage. Okay, so here are different data sets. Okay, and they're copied lots and lots of times over the different processes, over your individual computers. Okay, so if this guy fails, don't worry, the other two guys can pick up where we left off. The other one is in the fact that your individual CPUs can fail. All right? And so what you'll do now is, again, you have replication of your worker nodes. Okay? So now what you do is that for every worker, you make sure that there's some replication of each one of those workers. So if one of them fails, well, don't worry, that's okay. Another worker is there as backup and can pick up. Now, there's a variety of different strategies for doing this. Possibly the simplest way is just to have a massive level of replication going on. And then what you do is you essentially discard some of those guys. If you want to be more clever about it, what you can do is you can be continually querying these workers, and if one of them stops responding, you make an assumption, oh, okay, this one's died, and then you plug in and switch on another worker to carry out where it left off. All right. And other things you can do is you can introduce checkpointing, so that all the time you're keeping doing checkpoints, so that if there's a failure, then it can easily be another worker can pick up the work from the last checkpoint and carry on without a huge amount of loss of time. Okay, so again, none of this particularly. These two ideas are very well understood. It's just a matter of going out and actually implementing them. Okay, so whatever system we have, Hadoop is the one we want to aim for. Okay, we need to deal with large data sets using a massive but actually quite trivial level of parallelization. All right. In other words, we don't have to think about anything clever. We're just dividing up our data set. Any type of analysis where we just divide up our data sets and then just feed it out to individual processors, that's great. And there's a huge amount that can be done that way. Okay. As I said, the other point we need to do is we need to worry about the fact that such large clusters can encounter failure all the time. And again, you don't worry about that. Again, you want to be in a situation where you're using enough replication that you don't have to worry about this. And finally, and this is possibly the key point, is that ultimately somebody who wants to analyze this data actually doesn't want to be deeply concerned with any of these issues. In some respects, what you really need to do is to actually abstract away as much as possible all of the issues associated with running a large cluster of computers, right? So that ultimately it gets stripped down to bare bones, where somebody says, okay, these are the things that I need to provide. The system that I have does everything else for me. It does the parallelization for me. It deals with the communications that are existing between the different clusters, between the different disks, all of those kind of things. And finally, it deals with the fact that there's failures going on all the time. Now, Hadoop is one framework for doing all of this, and it's as you said, it kind of became the poster child of big data as a result. That said, it's certainly not the only game in town. Um, there would be more old-fashioned folk who would say, well, hang on, batch mode of operation, that's been around for a very long time. There's lots of stable software which goes and does that. Likewise, they are all sort of heirs to the throne of Hadoop. So, for example, there's something called Apache Spark, which I have to, put my hand up and say I was blissfully unaware of until about a month ago. And again, people are saying, "Oh yeah, this is the next big thing." All right. That said, one shouldn't knock Hadoop. There is a considerable ecosystem now that's based on Hadoop. There's been a lot of work done on there. So it seems, it's not unreasonable to say, okay, there'll be still lots of solutions that are really going to continue to be based on Hadoop. But, in particular, in industry, people are really sort of picking up on Hadoop now, and they're saying, okay, this is the way that we want to do things. So it's likely to be the industry standard for the future. So, as I said, before we actually get on to that sort of abstract layer, I think it is important to understand something about the internals of what's happening with Hadoop, because can sort of introduce the actual programmatic side of this, but that itself sort of presents. If I don't introduce some elements of what's going on with the internals, then it's something of a mystery. All right. So as I said, there's just two things that we need to know about. The first thing is how the data is stored. Okay, and that comes in something called HDFS. And indeed, again, when you do this and run Hadoop from a command line point of view, you can type in commands directly to HDFS. Right? It's an equivalent of ls in HDFS, for example. So the paradigm is that data initially for Hadoop comes as basically one big, large, whopping huge file. And then the analysis generally is based on individual lines in your file. Okay, so if you're dealing with flat text files, that's generally what's happening. You could do a bit more if you've got XML and stuff like that, but that's the sort of paradigm that you're working with. Okay, so the first thing that happens is that large file is then split and then distributed over the cluster. Right? They're stored as blocks, and those blocks are typically 64 megabytes in size. Okay, so ideally, what you want to do is you want to be able to divide your data into 64 megabyte chunks. If you have problems where you're trying to break it down into, say, smaller or bigger chunks, then that's going to be problematical. All right. In other words, if you're dealing with very, very small data sets, which come with very, very small units, which are much less than 64 megabytes, the example that we were talking about with PDB Hadoop, then you should try and concatenate them together, make them bigger, all right? If your data is much bigger than 64 megabytes, well, you may need to think about things in a different way. Again, HDFS deals with that issue of data redundancy. So actually, your data is stored typically 3 times over. Okay? And it's all built on the Linux file system to handle this. Right. Okay, so at this point, we're just about 29 minutes past. Before I get into talking about Yarn, I'm going to do the same thing that I did yesterday. And again, I've thrown a lot of things at you guys, so we're going to take a 1-minute break, and then we'll sort of pick up where we left off. All right, so talk to you again in 1 minute. All right then. So we talked about HDFS, but and that's going to deal with all of the issues about how do you actually store data in a distributed fashion across your Hadoop cluster. The other issue is how to actually how the actual work, computational work, is divided amongst the different processors that you have, right? And again, it's quite useful to know the basics of this, all right? So the first thing we'll do is just come up with a few definitions. So we'll say the job means the whole process that you need to execute, right? So I have this huge file which is 5 terabytes in size, and I want to find out all of the instances of the word sleep in it, all right? So that's a job that's going to run on many, many, many individual nodes, and they're all going to be running different executables, like what we see with the MapReduce stack. Right? And then there's an individual task, which is a subpart of that job. Usually it's executing one particular type of application, for example, a map or a reduce step. Right? And then we can talk about a container. So we also have individual nodes, and each node can actually have a number of containers. So a node could be a multi-core processor, which has got, so you can now have a container, a number of different containers running on that individual nodes. Yarn puts together something called a resource manager, one resource manager, which accepts those jobs and then allocates the tasks by communicating with node managers. So a node is something which is really, really physical rather than something that exists in software. All right? And then within each node, it sets up a particular application manager for each one of the tasks. Now what happens then is that the application manager may then request resources for the jobs. In particular, it's requesting containers. So let's sort of see this in particular, and this is a figure I've taken from an MSc report from Anna Gillan. So here's our resource manager. Now in this case, it's actually running 2 particular jobs, all right? One orange and one yellow. And so what it's doing is it's saying, okay, in this case, you've got an individual application manager, which is running for this particular job, all right? And what that needs to do is it needs to allocate a certain number of containers, which you remember is CPU plus storage. Now this guy is saying, okay, well I'll run one container which is sort of locally, and then I'll run another container which is over here because it's got some relevant data, and I'll use another one over here which doesn't even have an application manager. And likewise, we've got this other job running, which has got its own application manager. And again, it's allocating containers over here and over here, right? So as you can imagine, Yarn is actually quite a complex piece of software to arrange all of this that's going on here. And you might like to go and have a look at the original paper, which was written about 3 or 4 years ago by Vinapali. So far what we've done is you talked about HDFS, which allows you to actually store your data across many different processors. So again, lots of individual hard disk drives, and you've got plenty of redundancy there in the system. Yarn is the way for basically allocating the different jobs. And note again, Yarn can deal with all the different types of failures that occur as well. So that again, your job will actually get run even if there's a certain amount of fraction of failures that's going on here. With all of that in place, now we can actually get on with the business of actually doing calculations. Right? And to do this, we're going to use a formalism which is now 11 years old, originally developed in Google, called MapReduce. Right? And it is very much the main sort of computational engine for Hadoop. Now, people tend to look upon Hadoop and MapReduce in a sort of interchangeable way, but as you can see, Hadoop is a superset of MapReduce. MapReduce itself won't run without Hadoop, okay? But clearly, actually, when you get to the point of if you're somebody who's actually doing your analysis and you want to make use of these sort of tools, MapReduce is very much the part of Hadoop that you want to actually get on with things. Okay? And again, just to note, within Hadoop, this is not necessarily a particularly new idea. Again, MapReduce comes from techniques which were lifted from Lisp, but it's a formalism which sort of abstracts away almost everything until you get to just focus on the things that you need to actually do to do your type of analysis. All right? And what we're doing is in many respects, the most sort of simple way of describing it is going back to that figure which we created initially, where we talk about we've got some body of work that has to be done, and then we've got, so what we do is we divide that work, it's a big amount of data, into chunks. So there's a partitioning step. And then what we're doing is that's being passed to some sort of worker, which generates results. And then those results are then somehow combined together to give you your one big result. Right? Now, the whole idea behind MapReduce is to identify these different steps. Right? So what we now have is a map step, which is saying, okay, everybody who works in this framework has to feed in a particular data set. That data set then gets divided into chunks, and then the user needs to provide what happens here in this sort of this salmon pink color here, these worker nodes, what they're actually doing. The map step is saying, okay, we've got some particular type of analysis that's going on here. Then that data is passed on, and again, actually within MapReduce, this is a little bit more complicated than what we have here, but let's live with that for now. Then what happens is we've got another step where in some respect we've got to look at the outputs from these individual worker nodes, and now we have to combine them together in some way. And this becomes our reduce step. Right? So with MapReduce or Hadoop framework in place, all you need to do is to write the code that will be executed during the map and reduce phases. Of course, sort of sotto voce, what you need to do is generally you need to also write things in Java. All right. Now, as I said, things are a little bit more complicated than that if you want to think about optimizing performance. But generally, at first pass, all you need to know about are the map and reduce steps. And again, it's worth, there are lots and lots of description of how MapReduce works. I would say there's a good, concise explanation of all of this on the Hadoop wiki, which explains sort of very, very quickly what's going on here. Although, as you said, if you don't like that, there's plenty of other examples out there that on the web that you can look up. Okay, so the first thing to do, and I'm not going to actually sort of write down a specific, write things in Java. What I'll do is I'll just go through an example of this. So let's suppose we have one file with a list of Indian cities and their highest temperature on a specific day. Okay, so the top of this file, okay, Bangalore 29.2 Celsius, New Delhi 25.3, New Delhi 26.2, Bombay 30.1, and so on. So you've just got a huge long file, which is just like this, okay, which I might have thousands or millions of entries. And the thing we want to do is actually compute the average temperature in each city. So MapReduce is really tailored for doing these kind of calculations. So first let me talk about how the algorithm works. So as I said, with HDFS, your file gets split up amongst your nodes. Then there's a map step, and this is, so there's the map step, but and this is where you have to write a piece of code, and it's run over many different nodes over the different chunks of files that you have. So if you note, you've got all these chunks, all of them are being run in parallel, so you're cutting down the time that you spent here. So what you're doing is each individual node, each container, what it's doing is it's saying for the file that it has to work with, it says go through that file, which is much smaller than the big file that it initially got, and say, all right, every time I go to a new line, I'll look at the city name and I'll send out the city name and the temperature that I encounter. So if you imagine, after every one of these containers have run, each one will have generated a big long list of city names and temperatures. All right? In effect, they're concatenating out the file again. What then happens is that for each one of those individual lists, each list is now sorted on the key names. So it gathers together all the different key names, and then it puts together all those temperatures, and then they send them out. All right? Then actually most of the action is happening. The reduce bit part of this, again the thing that you want to do is to say, okay, your nodes are now set up again, your containers run, and again you might have a different number of containers this time. What you do is you say for each city that you have, each key that you have, you'll have a list of numbers. And now what you'll do is you'll compute that average over that list. And then what will happen is that you return and say, okay, you will have everything for every one city. So schematically, this is what's happening there. So here's our original data file, which is of some length, and it's being split up into chunks. So here's our map step. So this guy here looks through all of the lines of data that it had in this bit here, okay? And let's suppose that in this case, the first chunk was 3 entries in it, the second had 2 lines, first had 3 lines, 2 lines, 2 lines, and 2 lines, okay? So the first guy, what it does is it reads through it and it produces Bangalore 29.2, New Delhi 25.3, New Delhi 26.2. And each one of those guys are also running along like here. Then what happens is the map produce guy is now going to do a shuffle and sort. So what it's going to do is it's going to aggregate things by the keys, okay, which is in this case the city names. All right? So it'll gather together all the things which have got Bangalore on it. Okay, so now there are 2 entries with Bangalore on them. So let's create one list over here, which has got a key of Bangalore and then the 2 temperatures. New Delhi, as you can see, had 3 entries, and Bombay and Mumbai had 2 entries as well. So now each one of these lists then gets passed onto the reduce step. So the reduce says, okay, reduce step does, it says, okay, for each one of the lists that I've received, I'll actually compute the average of the data that I have. And then I'll return that. So it goes through this. In this case, as you said, there are 2 reduce steps. It might be there are 4, it might be that there are 3. Okay? So these guys will all get put together. The Bangalore average will be computed, the New Delhi average will be computed, the Bombay average will be computed, the Mumbai average will be computed. And then ultimately all those results will be sent back and put together. Okay? And there's a specific command where you can say, okay, just concatenate all those results together. Now, as I said, this is one implementation. The more sort of canonical example is to say, well, suppose I've got a big, long text file, and I want to find out the instances of every word that appears in the file. In that case, what you're doing is you're saying, okay, in this guy, again, you break it into chunks, and with the map step for this guy here, you again just produce a list which has got a word and just a 1. Okay? So it might be that a particular word appears many times, but it will appear, that key value pair will appear many times along in this particular list here. Then with the shuffle and sort, what you'll do is you'll end up with a big long list of words, and then a variety of 1s stored along here. And then the reduce step is effectively say, okay, count up the number 1s, the 1s that you appear for every list that you have. If I had, for example, a whole bunch of image files, say, astronomical data, I might be interested in saying, okay, tell me the instances of the brightness of stars that you see, all right? So in that case, the map step now says, okay, take my chunk of image files and just do some processing of each one of those images, and then produce some sort of image intensity, and then I put a 1 there, all right? Then you do some sorting. You again now produce a longer list, which is now where the key value is the image intensity. And then your reduce step is just saying, okay, again, I count off the number ones that have occurred. Okay. Now, there are some extra steps that are associated with this. There's something called combine and partition, which is there effectively to try and make to get some efficiencies out of this, because in particular, for example, if you find that your data is, say, heavily weighted by, say, in this example here, let's suppose that almost everything is, as you've got Bangalore temperatures, so you want to actually have that more evenly distributed. And likewise, there's a partition step which decides, okay, how many nodes am I going to have associated, or containers am I going to have associated with a different reduce step. Okay. But these are there basically to optimize the performance that you have. In reality, in your first pass, you just need to write your map step, you just need to write your reduce step. The other thing also to note here is that very much your analysis is kind of pretty much based on a line-by-line analysis of the data. And what's more, there's nothing here to tell you about the order of things. So for example, in here, the order of these temperatures has got nothing to do with the orders of the files that appear up here. Okay? Now, on top of this, so with MapReduce, this allows you to go and analyze extremely large data sets. And they said the paradigm is very much, your analysis is based on a line-by-line basis. Okay? There are tools such as Pig and Hive, which again are effectively running lots and lots of MapReduce jobs. Okay? So Pig is effectively a data processing language, which says, okay, transform my data into another different type of data. And what's more, you can run like little Python scripts, you can run all sorts of executables. And that, again, is assume that you're running things on a line-by-line basis. Okay? Hive is much more of a data query language, and it effectively produces an SQL-like interface. But the really, really neat thing about Pig and Hive is that it just works with the data that's there. All right? It doesn't try and create some sort of schema. It doesn't try and recast the data or copy it over and create some sort of relational database out of it. It just takes the raw data that's there, which is quite important if you've got several petabytes of data and you don't want to be copying that. The other thing to note, and just to sort of tie up with what we were talking about yesterday, is we can integrate this also with other packages. One we'll talk about here is OR, in fact. All right? So, for example, a company called Revolution Analytics have provided a set of tools, again, freely downloadable, you can make use of, called OR Hadoop. And again, we can go and take a look at that. If we go and look at that here, this is something provided by a tutorial provided by Hortonworks. I won't go through the details of how to do that calculation, but here, ultimately what you're doing is you're running a script in OR, and you've got a mapper function, and you've got a reducer function. All right? And again, as I said, all you need to do is provide a mapper function and a reducer function. And you see, as you can see down here, you can actually go and run whatever your MapReduce step is. So even though you could be running from your OR console, and you can hook yourself up to Hadoop, and you can actually go away and you can do a lot more analysis, huge amounts of analysis, very much on the fly. again, getting back to that model of analysing the data, modelling it, and then getting feedback from it, right? And repeating that process many, many times. The last thing I'd like to talk about with respect to Hadoop is a tool that myself and a student of mine worked on called Jamie, whose name's Jamie on this here, called PDB Hadoop. All right, and our initial idea was we wanted to have something which would help us get to grips with how Hadoop and MapReduce worked. In particular, what we did was we said, okay, we'll use something that we know about, and Jamie is actually has a background in pharmacy. So we wanted to look at protein structure data. So there are about 100,000 protein and nucleic acid structures that are stored in a central repository, which is called PDB. Just to show you this guy, it's a very nice website to look at. So as I said, nearly 100,000 structures, things like this, stored in here. So it's there, it's freely downloadable. The structures are stored in a number of different possible formats, but generally the ones that people use is a completely flat ASCII file format. And the entire data set is about 65 gigabytes long. Right. And one of the things we noticed was the fact that many structural biologists very often want to do a high throughput analyses of those structures. So two things that they do quite often is to say, okay, I have a new protein structure. And now what I want to do is I want to ask the question, well, will this protein actually bind to any of the proteins that exist in the PDB? Which is an important question because very often proteins do bind to each other. And the calculation for doing this is quite a computationally demanding one, and it requires you to look at the first step is looking at shape similarity, although there are many more iterations to that. Another one is to say, okay, I've got a specific sort of small molecule made up of, say, tens of atoms, and I'm asking, okay, will that bind to any of the proteins that exist in the PDB? And typically what you have is with all of these tests, somebody's gone away and written a piece of software which will do that, which will say, okay, give me an individual protein and I'll find if it can bind to another specific protein. Or here's a specific molecule, tell me if it binds to a specific protein. And normally what people will do is use batch software to sort of scale things up. Now what we thought was, okay, this is a nice example for us to go and look at how this would work if we could do this on Hadoop. And again, we thought to ourselves, well, hang on, there maybe will be structural biologists who might want to use Hadoop, but we don't particularly want to go through the pain of understanding how Java works. All right. So what we'll do is we wrote a little framework which sits on top of MapReduce, which allows you to run whatever your particular piece of software is to analyze the protein structure. Okay. Now, in fact, as it turned out, we only had to make use of the map step. We didn't need to use the reduce step, primarily because there's really no redundancy in the keys that you generate. Each of the proteins that you generate are unique. So it's very hard to say, oh, well, how do you combine that? All right. We noted also that because we were dealing with flat files, we actually had to do some pre-processing, which basically means actually taking those flat files and putting them all on one line. All right. So then they have to be unpacked and unwrapped as you go through every time. And what we've also done is we did that, and then we compared that with the sort of standard batch software, and we ran it on precisely the same cluster that we have now. And we did that for 3 different cases. So in the first instance, we ran it on sort of a Python script, which computes something called dihedral angles. And then we did another thing, which does another dihedral angle calculation, except it's an executable, all right? And then we did something which was, in those cases, we looked over the entire PDB. On the other hand, for the docking, we also looked at a much more hefty computational task where we looked at 1,000 PDB entries. Now, one thing that was kind of surprising was the fact that actually, particularly with with this Python script, it actually ran PDB, the Hadoop case, run much faster than the batch case. And indeed, we found generally that Hadoop is running much faster than the batch scheduler. We're still not quite sure why that's there, but that's still, we're quite pleased that that happened. We think it's because Yarn is actually able to make use of much more effective use of threading than the batch scheduler as it is. Okay, so at this point, I'd like to make. We're now. I'm running a little bit over, but I just thought I'd mention one last thing, which is I've spent the last 2 days talking to you about, or I've spent your time talking about Hadoop, and these are one of 2 tools that are out there that exists within the field of data science, and this field is rapidly expanding. What's really exciting about this is that increasingly there are larger and larger amounts of data which are not only just being generated, but that they're open and that they're freely downloadable. All right? Of course, free is still expense in terms of actually downloading the data. All right? And there are careers to be made in analyzing that data. Furthermore, it's clear that there are direct and tangible impacts for local societies that analyze these data. So, in particular, researchers in low and middle income countries really could capitalize on this. There's no reason why a researcher who's working in a low and middle income country cannot do cutting edge research on these type of data sets, except for 2 things. Number one, they typically don't have the infrastructure, and number 2, they don't have so much training. Okay? Well, solutions are actually pretty obvious. Cloud computing can actually provide you with that infrastructure to do that task. As long as you minimize the amount of traffic between a host institution and the client platform, you can do lots. All that's required there is the will to do it and the funding to do it. Likewise, in terms of the training, what we need are more and organized events like what we have here. And these are things that we want to work on. And these are which we want to work with people with here. And I'd love to talk with as many people as possible who are interested in these kind of issues. It's all about just having the will, just getting the funding to do this. It's all possible. Okay, so let me wrap things up by first of all acknowledging Andrew Harrison, generically known as Harry, who I've worked with for many number of years, and we've spent a lot of time talking about these issues. Anne Owen and Farhad Menon, they spent a lot of time working with me on doing things like clouds and doing stuff in R. Jamie Al-Nazir, he wrote PDB Hadoop, and he's my go-to guy on Hadoop. And Anna Gillen, who used to work at Paul Holloway and now works for Hortonworks, did a lot of work implementing Pig and Hive to analyze PDB data sets. Again, let me say thank you for your time.